Okay, so today in class we're going to explore sine, cosine, and their inverses. We're also going to touch on tangent a little bit, but our main focus will be on sine and cosine. Our standard is 12.2.1. So our objective for today is understand the basic concepts of sine, cosine, and apply them to simple problems involving right triangles. We have two goals. Our first one is just understand the basic concepts, and then the second goal is basically apply this to some more complicated incidents. So just kind of an open-ended question. Does anyone know what are sine and cosine?
I don't think I could explain it like mathematically.
Okay.
They do something with triangles.
Right, yeah, you're 100% right. So when we look at a right triangle, which is what involves sine and cosine, it is just simply the ratio of sides. So we've got the acronym SO, CA, TOA. And SO stands for opposite over hypotenuse. So let's say we're talking about this angle, that's theta. So the opposite would be here and the hypotenuse would be here. And this is adjacent over hypotenuse, and adjacent is the one connected to the angle. So this would be adjacent over hypotenuse, and then opposite over adjacent, but we're gonna talk about tangent a little later. Okay, that's exactly what I just said. So let's just jump into an example. If we have, I'll draw this a little bit better, that was a terrible triangle. If we have a 3, 4, 5 triangle, which we know is one of our special triangles that we use a lot in trigonometry. Let's call this 3, 4, 5, and if we wanted to prove those side lengths, we could do so using the Pythagorean theorem, but we know that that's accurate. Based on SO, and we're using this angle, what would the opposite of this angle be?
3.
3, that is correct. So if we have sine of theta, we have 3 over, and then what is the hypotenuse?
5.
5, that's right. So sine of theta is 3/5, and then if we do a similar thing with cosine, what is the adjacent side to this?
4.
4, that's right. And then we have the same hypotenuse as before, and of that triangle, so that will just be 4/5. And then if we do the same thing with tangent, we have opposite over adjacent. So we said the opposite is 3, right? And then the adjacent, similar to cosine, is 4. So tangent of that angle is just 3/4. 3/5, 4/5, 3/4, look at that. All right. So if we do the same process again, but with a different triangle, let's see if we can apply that. And we'll call this theta. And then we've got 5, 12, 13. Once again, another one of our special triangles, which we could prove using Pythagorean theorem, but we don't have to do that because we already know that it works. If I were to do the sine of this, what would the opposite be?
5.
5, correct. And then the hypotenuse is 13, right? 13. Cosine, we're gonna have adjacent, right? So what's that gonna be?
12.
12. And then the same hypotenuse as before, 13. And if we have tangent, we're going to have opposite over adjacent, right? So what's the opposite? 5, right? And the adjacent is 12, right? Perfect. So if we want to apply this a little more in depth, we can also use these functions, sine and cosine, to find the angle if we were given the sides. So we're going to do the same process but in reverse. And we know in trigonometry or geometry, however you want to look at it, we have two special triangles that are always going to have the same angles and the same proportions of sides. And that's a 1, 2, square root of 3 triangle, also 30, 60, 90 triangle, if you want to look at it based on the side lengths or the angles, either one. We know that the short leg of the triangle is 1. We know that the hypotenuse is 2, so the hypotenuse is double this leg, and this is square root of 3. And once again, we could use the Pythagorean theorem to prove that, but I'm not going to do that because we already know that it works. And then we have a 45, 45, 90 triangle, which will be like this, and in this one, the two legs are the same length, so these angles are also going to be the same. And then also we can write this triangle as, this isn't a very good scale, but 1, 1, square root of 2. These are equivalent because if we divided square root of 2, we're going to get 1. If we divided square root of 2 by square root of 2, we're going to get 1. And if we divided 2 by square root of 2, we're going to get the square root of 2. So if you see either one of these triangles, they're going to work interchangeably. So if we are trying to apply cosine and sine with this triangle, and we have the fact that sine of theta equals 1/2. We want to find theta. So what we're doing is the inverse of sine, which is called the arcsine. And in order to do this, we have to look at our triangle, and we have to decide, well, we know that sine is opposite over hypotenuse, right? So in order to do this, we need to find where 1 is the opposite. So which angle has 1 as its opposite? 30 degrees, that's correct. So, well, okay, we want to make sure that the hypotenuse lines up, which it does. So we can write that theta equals 30 degrees because based on what we said with opposite over hypotenuse, 1 is the opposite, 2 is the hypotenuse, so sine of 1/2. If sine of theta equals 1/2, theta will be 30 degrees. And then we can do the same thing with cosine of theta, but this time we don't want the opposite. What do we want?
Adjacent.
We want the adjacent, right. So if we want to find where the adjacent side equals 1, which angle is that going to be? 60, right. Correct. So
Could
theta,
it be 90?
that's a
In
great
any
question.
situation?
For our purposes, we're gonna stick to these angles because if we use this angle, our problem would be that like if we use this, our adjacent and our opposite and our hypotenuse are gonna end up being the same thing, right? Because this will be 2 as the opposite, and then the hypotenuse will also be 2. So there is a way to do this, and when sine equals 1, the answer is 90 degrees, and we're gonna look at that a little later.
I have a question.
Yeah.
It's kind of just a refresher. So is the Pythagorean theorem a squared plus b squared equals c squared?
Yes, so if we took 1 squared plus square root of 3 squared equals 2 squared, we know this is 1, this is, when you square root, you're going to get the number in the square root, right? So we have 4 equals 4, right? Good question. And then we could do the same thing with the other triangle if we wanted to. Okay, this one is a little more, well, it's the same process, but we're just using different sides. So if we're given that sine of theta equals square root of 3 over 2, how are we going to go about this? We need to find the opposite and hypotenuse, right? So if we're given that this is opposite over hypotenuse, we need to find the angle that square root of 3 is the opposite of. So, in this case, what would that be? 60, correct. And our hypotenuse is 2, so theta is going to equal 60 degrees. Good. Now if we did cosine theta equals square root of 3 over 2, we need the adjacent side, right? So in what case is square root of 3 adjacent? What angle is that adjacent to? 30 degrees, right? Like you said, it could also be 90, but we don't want the right angle. So this equals 30 degrees. Cool. Let's try it with our other triangle that we talked about. So we've got 45, 45, 90. 90. This is square root of 2, square root of 2, 2, or 1, 1 square root of 2, either way. If we put the sine of theta equals square root of 2 over 2. Now, this one's a little bit different. So we need opposite, right? And we need to find the angle that square root of 2 is opposite of. But if we look here, square root of 2 is opposite of this angle. But it's also opposite of this angle. So what are we going to do?
Would it just always be 45?
Right, either way. Either angle we choose, it's going to work. And if we did the cosine of theta equals the same thing, what do we think about that?
Same thing?
Same thing, exactly. 45 degrees. Perfect. Now, I want to go to Desmos here and show a little graph. So this is the graph of sine of x, which we're using up here, right? And we have when sine equals 1, which is going to be our y value up here, sine equals 1, this equals, it says pi over 2 over 1. Where is that coming from? Well, let's figure it out. So this is something called the unit circle. No need to memorize it because we can just use triangles and figure it out. And based on our unit circle, we have, it says 90 degrees and pi over 2 are the same thing. So how can we prove that? Well, we saw that sine, when it equals 1, based on our Desmos, it says when sine equals 1, we're at pi over 2, 1. So how do we know that 90 and pi over 2 are equal to each other? Well, we can use a proportion based on our unit circle. We see that pi and 180 degrees are equal to each other. They're just different units. So if we use this proportion, pi over 180, because these two things are equivalent, and set that equal to, say we want to find, we said that we wanted to prove that 90 degrees is equal to pi over 2. So we have, this is called radians. We're looking for radians, and we have degrees on the bottom. So 180, 90 degrees, we're all familiar with degrees. Right angle is 90 degrees. Now, we're trying to find what this 90 degrees is equal to. So we're going to set x as our radian over here. Now, based on how proportions work, we can cross multiply. So take this times pi, so 90 pi. And then we do the same thing this way, equals 180x. Now we want to get x by itself, right? So we're going to divide both sides by 180. This is going to go away, and this is going to turn into x equals 90 pi over 180. And we know that 90 over 180 is equal to 1/2, right? So you can write this as 1/2 pi, or you can write it as pi over 2. So as we can see, based on our proof, we figured out that pi over 2 is equivalent to 90 degrees. We're just in different units. And based on our unit circle, that is correct. If we look at the unit circle, we can see that our 4 main sectors, we have pi over 2 is equal to 90, pi is equal to 180, 3 pi over 2 is equal to 270, and then 0 degrees is just 0 radians. Or if we went all the way around, we'd have pi, 2 pi, which is also equal to 0 degrees. So, we did that already. If we want to do it the other way, we can use the same exact process. So if we have pi over 180, and let's say this time we want to find how many degrees is equal to pi over 2. I know we just proved that pi over 2 is equal to 90 degrees, but we just want to prove that the process works in reverse. So if we cross multiply, pi x equals 180 times pi over 2, which is equal to pi x equals 180 divided by 2 is 90 pi. And then these pi's we're going to divide, so they're just going to cancel out. X equals 90 degrees. And as we saw on the unit circle and our last example, pi over 2 is equal to 90 degrees. So let's try to do this without me. So if we want to convert 30 degrees to radians, where should we start? Well,
Can you start us out?
yes, absolutely. So remember, if we look at the unit circle, we have these two things equal to each other, right? And you could use this or this or this, but this is easy because pi is not in a fraction. Like all around here, pi is in a fraction. So we want to set up a proportion that says, pi over 180 equals something. We know that we can use this because these are two things that are equal to each other. So this compared to this is the same as this compared to this. And we want to go from 30 degrees to radians. So we have to do something with that 30. Where should we put it?
On the bottom.
On the bottom, right? Because this is degrees, we want to keep these in the same place. There are other ways to work proportions, but this is the simplest way, I think. And then we're just going to put a variable. And then where do we go from here? Cross multiply, that's right. So 180 times x equals 30 pi. And then this is just our algebra step, right? Divide by 180. Now we have x over 30 pi, x equals 30 pi over 180. And we know that this is 1/6 if we reduce it. So then we have 1/6 pi, or we can write that as pi over 6. Now, based on the unit circle, pi over 6 is equal to 30 degrees. Let's see. Oh, I guess I didn't use that example. But pi over 6 is equal to 30 degrees. So if we look at this triangle again, we had 30, 60, 90, 1, 2, square root of 3. If I were to put, instead of 30 degrees in here, we could also write pi over 6. It just depends on what the question asks. So if it wants radians, we want all the degrees to be in terms of radians, so we can convert them like this. So if it's 30 degrees and we know that it's a 1, 2 square root of 30 triangle, we can replace the 30 degrees with pi over 6, and same here. With the 60 degrees, we're going to figure out what 60 degrees is equal to in the next problem. So This process is in reverse, right? So how do we want to start a problem like this?
90 degrees.
Remember, we have our proportion. So pi over 180, two things that are equal to each other. Now, we have radians, right? So do we want to put that in the numerator or the denominator? Right. What is it? Pi over 3? Pi over 3. And just a variable here because that's what we want to figure out. Now, what do? Cross multiply. Pi x equals 180 pi over 3. And 180 divided by 3 is 60. So pi x equals 60 pi. Pi's cancel. We are left with x equals 60 degrees. And if we go back to the unit circle just to check ourselves, we can see that pi over 3, what we started with, is equal to 60 degrees. So we did it right. Now, what time are we at?
21:25.
Oh God, okay. Okay, so that concludes our lesson for today. These were just extra if we had time, but class is over, and hopefully we can apply our concepts to the homework.